All right, so this video is on Lewis structures for if you missed the day or a couple of days when we were learning about how to draw Lewis structures. All right, so what Lewis structures are is they're a way to draw molecules. Previously, we learned about single Lewis structures, and what single Lewis structures are is when you get the periodic table. Um, Right, there's hydrogen, below it lithium, beryllium, below those sodium, magnesium, and I'm just looking at my periodic table for this. There's all the transition metals that happen in the middle here, the transition metals. We aren't going to care about those. Then we've got boron, this beryllium, sorry. Boron, underneath that, aluminum, carbon, silicon, nitrogen, phosphorus, oxygen, sulfur, fluorine, chlorine, and over here, helium, neon, argon, and whatnot. And these go further down. I just won't take the time to draw those out right now. Okay, so single Lewis structures, what those are is, just if you remember, we just count how many valence electrons there are. And those single Lewis structures, how many valence electrons, we just count the columns, but skip the transition metals. So we skip this whole area here. So this has 3, this column has 4. And then unlike charges, right, when we have the charges, they go back down to -3, -2. The ones on the left are positives. But this is different than charges because we just count 5, 6, 7, and 8. And that is how many valence electrons anything has. So anything in this column with nitrogen, phosphorus, all that will have 5 valence electrons. Any of the halogens, fluorine, chlorine, right below that is bromine and iodine. We get bromine, we get iodine. All of the halogens have 7. All of noble gases have 8. Note helium is an exception. It just has 2 because it's not far enough down yet, but don't worry about that. We won't really do anything with helium. Okay, so that's single Lewis structures. So if I were to draw the single Lewis structure of these, everything that has 1, we just put 1 electron around it. Everything that has 2, we put 1 electron. The second electron goes on a different side. Second electron goes on the other side because, right, electrons repel each other. They can't be right next to each other, especially if they have an option not to be. The third row, let me just separate these all out a little bit. Separate these all out, just drag them down a smidge here. Just drag it down. Okay. And okay. So the third column over here, so we've skipped the transition metals, right? We do 1, 2, 3. The fourth column continue to go around 1, 2, 3, 4. The fifth one, we still do the same process. 1, 2, 3, 4, but the fifth one pairs up. Sixth one, 1, 2, 3, 4, 5, and 6. Those 2 pair up. 7, 1, 2, 3, 4, 5, 6, 7. And then 8, 1, 2, 3, 4, but then 5, 6, 7, 8, they all pair up. What's important about this is because now in Lewis structures, we care about how many lonely electrons there are, because electrons cannot be lonely. They are like your friend who must always be in a relationship. You know, you always have that one. There's always that one friend. That friend is like an electron. Electrons cannot be lonely, so we always want to find how many lonely electrons are there, and we've got to pair them up. All right, so Lewis structures, the way they'll work is I'll come over here, do this practice, methane CH4. So I'm going to, this is a practice sheet that was passed out in class. If you missed the lesson on Lewis structures, you also missed this practice sheet. So it's a perfect way to practice. All right, so I'll show you how to do these using this methane CH4, maybe, if I can blow up my screen a little bit. There we go. Okay. So methane CH4, the way we do Lewis structures, there's typically one of one atom and multiple of a different element. What happens there is we take the one where there's just one of them, and we put that one in the middle. And then we take the one where there's multiple of them, and those go around the outside in fourths. So hydrogen, 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 hydrogen. And because there's four sides of every one of these, as we can kind of tell by the Lewis structures, there's four sides, one side, two side, three side, four side. There's four sides to all of these atoms. So we space them out in fourths. Okay, what's next? Once we have them spaced out, then we just take all of these and we put the single Lewis dots around them. So that's what we just did up top here. That's why I started this video like this. So we put the single Lewis dot around them. So the first one here, carbon. This carbon, well, we count how many valence electrons it's got. So it's in 1, 2, skip the transition elements, transition metals, which are these metal ones, skip those. 3, carbon is in the column that has 4 valence electrons. So carbon, we do 1, 2, 3, 4. Awesome. Then we look at hydrogen. Well, hydrogen is over here. It's in that first column on the periodic table. So that means hydrogen will get 1 valence electron each. So each of our hydrogens, 1, 1, 1, and 1. All right. What's next is electrons. I mentioned this earlier. Electrons cannot be lonely. That's why I highlighted all of the ones in blue here. I'll highlight the one on hydrogen because that's what we're dealing with now. Electrons cannot be lonely. What I mean by that is you see how on like nitrogen here, there's these two, those two that are already in a pair. When we went through and did the single Lewis, those got paired up. On oxygen, there's a pair here and a pair here. Fluorine, there's a pair, and a pair, but only one lonely electron. The noble gases are already, they have 4 pairs. Since the noble gases have 4 pairs, they don't have any lonely electrons, so the electrons don't need to pair up. That's why noble gases don't react, hence the name noble gases. So since all electrons need to pair up, here's what we do. All right, this is a lonely electron on the hydrogen. Oh, but here's a lonely electron on the carbon. Well, electrons can't be lonely. What do you think they'll do? They'll pair up. The lonely electron on the hydrogen, there's a lonely electron on the carbon. Electrons can't be lonely. They pair up. Lonely on the hydrogen, lonely on the carbon. Well, they can't be lonely, so they pair up. You might guess the last one, lonely electron, lonely electron. Electrons can't do that, so they pair up. What this looks like then is we then take this, we take this whole structure, and I'm going to redraw it, but instead of the arrows and electrons, every time we get 2 electrons here that would pair up, so anytime we get this whole section, shared electrons, when they pair up like that, because what truly happens is it goes both ways. They share. All right, they go both ways. They share. So the lonely electrons are paired up. What we do is we replace this whole thing with a bond. So you replace 2 electrons that are being shared with a bond, and that's just a line. 2 electrons here with a bond, that's a line. All right, that's this pair here, that's that pair that's getting shared. The one over here on this side, that's 2 electrons getting shared, so we replace that with a bond. And the one on the bottom, that's 2 electrons getting shared, so we replace that with a bond. I'll do that in the same color. Okay. So now we've taken all our shared electrons over here. Sorry, this looks a little bit messy at the moment, but then we've turned it into this nice looking Lewis structure here. This is our final Lewis structure for methane. Okay. So what happens is these used to be the electrons, right? Carbon had 4 around it. Each hydrogen had 1. Carbon had 4. 1, 2, 3, 4. Each hydrogen had 1. 1. You'll notice here, instead of this electron being on top of the hydrogen like it was on the left here, I just moved it around. We're totally allowed to do that. You can move them around as long as we maintain how many of them are paired and how many of them are lonely. Then over here, carbon and hydrogen, carbon and hydrogen. You'll notice these hydrogens on the top and on the left are the same. We just moved the lonely electrons around. We're allowed to do that. All right, so that is, you can see each of these lines represents 2 electrons, one from the carbon, one from the hydrogen. They're just being shared. Because our last step is to make sure that every element has 8 electrons. Does it have 8 electrons? The one exception to that is hydrogen only needs 2 electrons. So we have to go around and check. Does every element have 8 electrons around it? But does each hydrogen have 2 electrons around it? Let's start with this carbon. The carbon, it started with 4 electrons, but now because of these bonds, and I'm going to just redraw these with just the bonds here. But you remember how each of these bonds, right, it's one from carbon, one from hydrogen. So each bond represents 2 electrons. So carbon is going to have 2 electrons from that bond. It'll have 2 electrons from this bond, 2 from this bond, and 2 from this bond. So if we add all those up together, there's 2, 4, 6, and 8. Carbon has 8 electrons, so carbon is good. Now we need to check each of the hydrogens, that each hydrogen has 2 electrons. Well, each of these hydrogens has 1 bond around it, so that's 2 electrons. That hydrogen's good. This hydrogen has this bond, which is 2 electrons. That hydrogen's good. This one has this bond around it, 2 electrons, so that's good. This hydrogen has this bond right next to it, 2 electrons, so that one's good. All right. So we have now successfully concluded that each of these has 2 electrons around it, but the carbon has 8 electrons around it. So we are all good. That tells us that we are done. This is the Lewis structure of methane. I don't know where the methane went, but methane, CH4. All right. Perfect. That's how we draw Lewis structures. Let's practice a few more on a few of these other compounds. So let's try hydrochloric acid now, HCl. So hydrochloric acid, HCl, what this looks like, we're going to find out. All right, hydrochloric acid. So there's a H and there's a chlorine, hydrogen and chlorine. When there's only 2 atoms, remember the previous one, there's 1 carbon and 4 hydrogens. So we put the carbon in the middle and the hydrogens around it. But when there's only 2 atoms, an H and a Cl, it doesn't really matter. We just put them there, H and Cl. Okay. Actually, for learning purposes, I'm going to move the Cl over here. We'll find out why later. Okay. So that was our first step. You just place the atoms there. The next step, right, we do our single Lewis structures. So hydrogen, it's in this first column over here, so it gets 1 electron around it. Hydrogen gets 1 electron around it. Chlorine, well, if we look at the periodic table, chlorine is right over here. Chlorine is in the column that gets 7, right? Remember, we just counted 1, 2, skip the transition metals, 3, 4, 5, 6, 7. Chlorine gets 7 valence electrons. So we put them around chlorine, 1, 2, 3, 4, and then we pair them up, 5, 6, 7. Okay. Oh, but here's an interesting thing. Chlorine has got, right, 1 lonely electron. Hydrogen has got 1 lonely electron. Well, what do you think they're going to do? They will pair up with each other. Okay. But here's how we can see this maybe more easily, because what I'll do here is for chlorine, instead of having this lonely electron really far away from the hydrogen, I'm going to take these electrons on the chlorine and I'm going to just respace them out So the lonely electron is closest to the hydrogen. Remember, we're allowed to do that. We can redraw these and just turn the molecule around. Well, the hydrogen, I'm going to do the same thing. I want to turn this molecule around so this electron is closest to over here. So I'm just going to turn the molecule, put the electron right there. Okay, so then lonely electron and lonely electron, they pair up. Okay, that's it. So we've paired up all our lonely electrons. The only thing left to do now is see if there's 8 electrons on everything, but for hydrogen to see if there's 2 electrons. For hydrogen, is there 2 electrons on all of these? So chlorine, well, there's 2, 4, 6, and this bond counts as 2, so 8. Chlorine is good. So chlorine is good. Hydrogen, well, we only need 2 on the hydrogen. It's right next to this bond, and this bond counts as 2, so hydrogen is good. All right, that tells us that we are good, and this is our final Lewis structure. Okay, let's keep going then. Let's do just a couple more. I'll do one more from this side. So let's do phosphorus trifluoride, PF3. This phosphorus trifluoride, PF3. Okay, so now we've got phosphoruses, or a single phosphorus, and we've got fluorines, 3 of the fluorines. So phosphorus we'll do there. Fluorine, there's 3 of them, but remember molecules have 4, or atoms have 4 sides essentially, so we have to space them out around the sides. So let's do 1, 2, 3. And we'll reposition these later, but I want to show you how we reposition them is why I start with them here. So phosphorus, if we look at our periodic table, phosphorus we find right here. Here's our phosphorus. Phosphorus is in the column with 5 valence electrons. So phosphorus gets 1, 2, 3, 4. Then we pair them up, 5. Fluorine, if we look over here, fluorine is in the column over here. Here's our fluorine. That's in the column with 7, right? 1, 2, skip the transition metals, 3, 4, 5, 6, 7. So fluorine has 7 valence electrons, and that's for each of them. So 1, 2, 3, 4, pair them up, 5, 6, 7. Other fluorine, 1, 2, 3, 4, pair them up. Oh, I don't know what happened there. 4, now we pair them up, 5, 6, 7. Last fluorine, 1, 2, 3, 4, pair them up, 5, 6, 7. Okay. Let's do the same thing that we've done before. Lonely electron, lonely electron, lonely, 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 lonely. Okay. So what I'm hoping you're starting to see is that the phosphorus, there's 3 lonely electrons, but then around the phosphorus, there's 3 fluorines that each have 1 lonely electron. So I'm going to delete the highlights just for the sake of ease here. All right, we'll kind of notice these 2 might pair up. These might pair up, 1 and 2, but what I'm going to do with this fluorine is I'm just going to turn it around so we have 1 lonely electron is closest to the phosphorus. Okay, so then these will pair up. But then the phosphorus, the last lonely electron's on the bottom, but this fluorine's on the top. Here's what I'm going to do. You just take this whole fluorine and you move it to the bottom because we're allowed to do that. We can move things around. As long as we don't change what they are, we're allowed to move them around. Same with the electrons. Because the lonely electron was on the left, but it's going to need to bond on the top, I'm just going to move it around so the lonely electron's on the top. And now these lonely electrons can pair together. So what we do, or what we get when we redraw this, right, we've got the phosphorus in the middle with the 2 electrons on top. Then we've got a fluorine on the right, fluorine on bottom, fluorine on the left. there's a bond between the phosphorus and each of the fluorines. Then each fluorine has 6 electrons around it, 3 pairs. All right, since we don't have any more lonely electrons, that means we're probably done. So we'll just check to make sure now that we have 8 electrons. Since there's no hydrogens, all of them should have 8. So phosphorus, well, phosphorus has 2, 4, 6, and 8. That's 8 total. Perfect. Phosphorus is good. Fluorine, 2, 4, 6, and 8. 2 from each of those places, so 8 total. Perfect. 2, 4, 6, 8. Perfect. And then this fluorine, 2, 4, 6, and 8. Perfect. Okay, so we're done now. We are done. This is phosphorus trifluoride right there. All right. Let's move on then to do a couple that are a little bit harder. Just a little bit harder. So I'm just going to do 2 more, and I'll make them pretty fast. So let's do this formaldehyde up top, CH2O. Yes, this is the formaldehyde you're thinking of. So formaldehyde, CH2O. All right. So I tell you on the other sheet, but the carbon goes in the middle. Carbon is central. That's just kind of a fact of life. Carbon always goes in the middle. And then H2 and O. Okay, so we've got 2 hydrogens and an oxygen. Doesn't really matter where we put them because we'll figure it out later. Okay, then single Lewis structures. Carbon is it's right over here. It's in the 4th column over, so it gets 4 valence electrons. All right, carbon gets 4 valence electrons. 1, 2, 3, 4. If we look hydrogen, if you remember, hydrogen has 1 over here, so hydrogen just gets 1 valence electron. I'm going to, instead of putting it on top, I'll just put it closest to where it has to bond. We'll think ahead. Hydrogen. Okay, then oxygen is over here. Oxygen is in the column with 6 valence electrons. So oxygen gets 6. 1, 2, 3, 4, 5, 6. Pair them up. Okay. So now let's start pairing up lonely electrons. So here's 1 pair. Here's another pair. Here's another pair. Oxygen has 2 lonely electrons. So what'll happen is the carbon and the oxygen will actually share 2 pairs of electrons. So we replace a shared electron pair with a bond line. Replace a shared electron pair with a bond line. Replace a shared electron pair with a bond line. But since the carbon and the oxygen share 2 pairs, what happens is they actually share 2 bonds. This is called a double bond. It's called a double bond. When there's 2 bonds right here, we call it a double bond. It's possible to have a triple bond as well. Quadruple bonds just don't happen. That's too many electrons packed in tightly, but a double bond does exist. Okay, so all we have to do now is to make sure that, right, electrons are all negatively charged. They repel each other. So we just space these out so electrons are as far away from each other as possible. Right, these are pretty close. These electrons down here in this bond will push these electrons, they'll push them up. But these electrons here will push these electrons up that way too, until eventually the electrons from these bonds and the electrons from these bonds, they will repel each other. So since there's 3 kind of regions of electrons, there's kind of 3 regions of electrons. 1 region here, there, and here. There's 3 regions, so we'll space them out in thirds. What I mean by that, carbon, right, we'll have the oxygen up here, a hydrogen down here, and a hydrogen kind of over here. But remember, the oxygen comes with these 2 pairs of electrons. These are called lone pairs or unshared pairs, either way. You see how the oxygen and the hydrogens are kind of spaced out in thirds. This is actually our Lewis structure. And the oxygen, I've even taken the pair of shared electrons, this pair and this pair, and I've spaced those out to be here, here, and here. So they're spaced out too. So this is our Lewis structure of CH2O. Is right there. Okay. I think there's one more I wanted to do with you. Yes, SiO2. So the silicon dioxide. This is the last one that we'll do, and I'll do it kind of quickly because I know this video's getting a little longer. Okay, so silicon. Silicon, if we look at the previous sheet, silicon is right here. Silicon is under carbon. It's in the 4. So silicon and carbon are like each other. Oxygen is the other one. It's in the column with 6. So silicon and oxygen. Silicon's got 4. Oxygen's got 6. So silicon. Since there's one silicon and 2 oxygens, I'm going to put the oxygens on opposite sides. Silicon has 4. Oxygen has 6. So 1, 2, 3, 4, 5, 6. Okay. Then the silicon, well, those two will pair. Those two will pair. Okay, so we'll have a double bond between the silicon and this oxygen, since there's 2 pairs that are shared. This oxygen over here, what I'm going to do is I'm going to just completely redraw the electrons to take the 2 lonely electrons on the left and on the bottom. Because essentially what I'm doing, and I'm going to see if it'll let me actually do this. Well, let me rotate it. I don't think so. What it'll let me do is if I just rotate this to take the electrons, instead of on the left and bottom, I'll put them on the top and on the right, because these electrons will be will pair up. These lonely electrons will pair up. Okay, so then what we get is this. Right, you take 2 electrons, or you take the electrons that are shared and you replace them with a bond line. You take the electrons that are shared and you replace them with the bond lines. There's a double bond there. Oh, but now we have the same thing on the other side. You take the electrons that are shared, replace them with a bond line. Take the electrons that are shared, replace them with a bond line. Okay. So now we have the silicon and 2 oxygens, or silicon dioxide, and there's 2 double bonds here. We'll then just take the electrons around this oxygen and move them so they're spaced out as far apart as possible. All right, so there's the 1 bond and then 2 pairs of electrons, so we'll put them in thirds. 1 bond and 2 pairs of electrons, so we'll put them in thirds. Assuming my computer wants to cooperate. Okay, here we go. So we put them in thirds, and that is silicon dioxide. Now, last thing, right, check to make sure it has 8. So there's 2, 4, 6, and 8. 2, 4, 6, and 8, right? Because each bond is worth 2, but there's 2 bonds around it. Silicon, 2, 4, 6, and 8, because each bond is worth 2. Oxygen, 2 and 4, then 6 and 8. Okay, so all of them have 8 around them. Good, that's what we need. Perfect, we're done. All right, sorry for the kind of lengthy video. I will stop it now. But let me know if you have any questions. Good luck.